get caught up on that. The biggest feedback I'm getting is that people are looking at some of these charts they're producing and they're just not looking very awesome because the data is too small and things like that. What do you guys, talk to me, how are your charts looking?
I seem to be converging after like 2 instances.
Ah, that's,
I might be doing something wrong.
okay. How about you guys? Do you get a nice smooth slope into convergence or do you get bad, bad, good on your charts?
Bad, bad, good, bad, 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 good.
Oh, it jumps up and down? And then does it get stable or does it just jump up and down forever?
Finally, it's very stable.
So after a lot of training, it stabilizes and continues on. Okay, that's what I would hope for. So I got to admit, I picked this data for its properties. I didn't really make a chart and see how it looks. So I don't know for sure that the chart you're about to make is representative of the one you'll get from data in general. And I like doing that partly because then whatever happens, we got to go back and look at it and explain it and figure it out. And there's a lot of learning that occurs there. So let's look at and figure out what's going on. But at the same time, that picture you saw in the book is probably more representative of the theory and the learning that I want you to get out of it. Does that make sense? Okay, yeah.
Since we're doing root mean squared error on a categorical variable with 4 different options, should our values all be between 0 and 4?
Somebody brought that up and I was supposed to fix it and I totally forgot. I apologize. So yes, I didn't divide this data for you because I'm making you deal with data. And so you have features and labels in the same data set, and this last one is the class label, the label. Did you catch that? Okay. So you have to divide the data yourself. The other thing is, this is a categorical attribute, which means there's some number of categories. Root mean squared error really doesn't make sense in this context. So root mean squared error is a regression metric. Let me draw a picture to illustrate what I mean. So if this is your data and this is your model, what is root mean squared error? It's the average of how much the data deviates from the prediction. And we compute that by measuring the difference between the target and the predicted in every case. And we square it, and we sum them up, and we divide by n, and then we take the square root of it, and that's root mean squared error. Okay. In the case of categorical values, well, let's just use the ones from the data. We've got negative compensated primary and secondary. Negative compensated primary and secondary. Okay, so I guess your data looks like this. Ish. I mean, every instance is going to be one of those categories, and you're going to fit some kind of a model to it that kind of tries to hit the data somehow. And then when it makes a prediction, the model is going to be snapped to the actual values. Now, if we were to measure difference between target and prediction, well, after it's snapped, that's going to be a 0, right? Hopefully they're all zeros. But if they're not 0, then what do you do? I guess what I'm saying is that wrongness any worse than that wrongness? Meaning, if the true answer is n, what did n stand for? Negative. If the true answer is negative and you say secondary, is that worse than if the true answer is p, positive, and you say secondary, primary, and you say secondary? Yeah.
But if you non-candidate, isn't it already like there's no ordinality already?
Yeah. So basically I'm having a hard time visualizing this. But here's what it comes down to is root mean squared error doesn't make any sense with a categorical label. So my instructions were flawed, and thanks for pointing that out. What we really need to do is measure misclassification rate. So for MSE. So in fact, this would be a good point to emphasize just as sort of a test review thing. Root mean squared error is for regression. Regression is when you're fitting to continuous values. Misclassification rate is for classification. Classification is when you're trying to predict categorical values. So change my instructions to say misclassification rate. Now, there is something called Hamming distance, which I need to mention. Hamming distance. Has anybody heard of Hamming distance? Okay. So the idea of Hamming distance is if you're right, meaning we'll say that's right because it's so close that we'll snap to the same value, then your distance is 0. That makes sense, right? And Hamming says if you're wrong, your distance is 1. So that is distance of 1, and that is a distance of 1. And we're going to claim that's fair because these categories, as far as the neural network knows, have no meaning. They're all just different concepts. Okay, so when would one use Hamming distance? Basically, whenever you have categorical values, you use Hamming distance. And when you have continuous values, you use Euclidean distance. Here's an interesting thing. Imagine a database table where you have a whole bunch of columns that are continuous and a few columns that are categorical, where for some reason orange means categorical and black means continuous. Then suppose you have some patterns or some rows in your database and you want to say, how similar are these two rows? Do you see how Euclidean distance doesn't quite make sense? What's Euclidean distance? It's the sum over I of, switch to text mode, x minus x squared and then we need to square root the whole thing. That didn't quite come out right. And I should put an I there and an I there, and I'll boldify that hat a little bit more. Okay. Do you agree with me? This is the equation for Euclidean distance that you all know and love. Okay. In this case, I'm using x minus xi hat. I'm suggesting that one's the prediction and one's the target. And if we're measuring the different distance between the prediction and the target, there's the normal distance equation. Okay, you could just as well replace this with a and b if you're measuring the distance between 2 points, or whatever you're measuring distance for. Now, if you're measuring the distance between 2 rows in a database table, that makes sense as long as all the numbers are continuous. What do you do if some of the numbers are not? Well, suppose we were to plug in Hamming distance here. So we say, for the categorical attributes, we'll set it to 1 if they're different, 0 if they're the same. And for the continuous attributes, we'll set it to the difference between them and square it. And now we have defined an arbitrary distance metric that can work with arbitrary data, whether Euclidean or categorical, or even a mix of them. See how that could work? Okay, well, here's a question. Why 1? Well, is 1 the right distance between 2 values that have differing meaning?
I mean, if 1 means it's wrong and 0 means it's not.
Yeah, why 1? Because 1's a good number. Why not, right? I mean, what number are you going to pick instead? 3 is good too. I like 3. Pi is a good number. But it's really 1 because that's kind of saying we don't know what number to use here, so we're going to say it's off by 1, and you can scale it by whatever's appropriate. If you were measuring distance, then kind of the scale of these attributes totally dominates the distance metric anyway, right? If this unit were measured in micrometers and this one were measured in parsecs, the micrometer distance presumably is going to be really large and the parsec thing is going to be really small. And when you measure the total distance between two vectors, the micrometer one's going to utterly dominate the distance. And so you can see the distance is totally subject to how you scale the attributes anyway. Usually when we do learning, we kind of scale everything so it's in approximately the same range. If we normalize all the continuous values to fall between 0 and 1, and then we're using Hamming distance for the categorical values, kind of feels like we're doing the right thing, doesn't it? And then we can measure distance between patterns and maybe it's somehow meaningful. Okay, well, interestingly, Hamming distance is kind of the same thing we're doing when we measure misclassification rate. Because we're saying, are you right or are you wrong? And every time you get it wrong, we're going to add 1 to our error, right? And if we square that 1, it's still a 1. And then if we take the square root of it at the end, well, now we've confused ourselves. So you usually don't square root it at the end. So you might say misclassification rate is analogous with mean squared error, not root mean squared error, if you are using Hamming distance on categorical values. Does that make sense? Okay, great. Now I think you were going to ask a question about it, but I think I just basically said forget root mean squared error, we're using misclassification rate. Have I answered all your questions on that? Okay. When last we were talking, I think we were talking about how the chart looks. And does your chart look kind of like this? I can't draw very straight. Is that what your charts look like? Because that's a very boring chart, isn't it? I mean, we'd kind of like a chart that looks a little bit more like that-ish, right? Because then we can at least see some variance in it. So let me ask you some questions. Are you measuring per epoch of training? Or are you getting a bad chart when you're measuring per pattern presentation? Nobody wants to answer that question, I see. Okay. Well, let's assume you're doing it per epoch, and I'm going to recommend, what if you measure the error after every single pattern presentation? Now, that would be deathly on the MNIST data set, right? Because there's so many patterns in the training data that would just kill your performance. This data set's pretty darn small. Can I recommend we measure error after every training pattern presentation, and then I think the chart will look more like this? Anyone want to refute that? Yeah.
I'm already doing that and I'm still having those issues.
Ah. So you're measuring after every pattern presentation, and it's one pattern presentation, and you're getting great accuracy?
After like 2, it's just like, oh, everything's negative, I guess. So.
Ah, okay. So
On
with
this, it looks normal.
here's what's happening with this data set. You remember how the baseline algorithm, there it is, does a really good job with this data because 90% of them are negative. So what's happening is the biases in the neural network train really fast. And so as soon as those biases train, then it's approximating exactly what baseline's doing. Has anybody ever been able to beat baseline, or are you just getting baseline with your neural network?